If we want to accelerate an object, we push on it. We apply a force, we push on it with some force, it has mass, and that will cause it to accelerate by Newton's second law. Okay? But how do we apply that law to something that's pivoting, something that's spinning around an axis? So for example, what if I have a playground toy called merry-go-round, which is basically a big disc so we'd be looking top-down view, looking down at it. And it's a big disc with some handles all over it that's pivoted at center, and it could spin around. And I really enjoyed these as a kid. They don't have too many of them, probably because they're dangerous. But you can get on them, and then someone spins it around, and you get to play on it and sometimes fly off and just try and see how long you can stay on it. Well, to get it spinning, you have to push on it. But pushing on it is much different in this case than pushing on it in this case. So for example, if I try to get it spinning, I could push on it like that. That's a force, but is that going to make that merry-go-round spin around? It's not. That's obviously I'm not going to make it spin if I do that. I could push on it like this. Now that might get it spinning somewhat. But really, if I push on it right tangent to the surface, that's got to probably make it spin the best, okay? Because I want it to spin around that axis. And so not only do I care about how big of a force I push, I care about the angle at which I push it at, okay? Now, another thing is, let's say something's really heavy, and I want to get it turning. Well, I could attach a big long rod to that thing, and I could push here, and it'd be much easier to turn that rod, or to turn this thing. So by making a lever that sticks way out and pushing on it, I can make this thing spin better. Now, so what we see is that to make something spin, to speed up in rotation, I need a big force. I need that force to be tangential to the direction of spin, so that this circular motion. And I need to push as far out as I can be. So how do we include all that? Well, first of all, we give it a name. We say torque, or give it a Greek letter tau. It means torque. Okay? And it's the equivalent of force in rotation. In fact, I call it the rotational force. This is rotational force. And it depends on the size of the force, how big that force is. Okay? It depends on how far out you're pushing. And then it depends on a certain angle. Okay? It depends on how perpendicular that force is to where it's being pushed. So if this is the R, I'm pushing right there. I want to be as perpendicular as possible to that R. Okay? And so what we do is we can relate those things and use sine of the angle between F and R. Excuse me. And to make that clear, why is it sine of theta? Is if I look at these two vectors, noting that what I really want is to have them perpendicular. Well, I can redraw those vectors. Here's the force vector, and here's the R vector. And if they're perpendicular, that means the angle between them is 90. I'm writing it wrong. 90. Okay? Here's the force, and here's the R vector. If the angle is 90, well, sine of 90 is 1. And so I've maximized the amount this force is going to cause it to rotate. Okay, so the sine of theta is the angle between these two vectors. Now, just like work, if you remember, work was equal to force times some displacement, and we had a cosine of theta, which really meant we just want Fs ds. We wanted the amount of the force in the direction of the displacement, and so we used a cosine of theta being the angle between these two. Here we don't want a force to be in the direction of the radius. We want a force to be perpendicular, and that's why we use the opposite. So we could also say that this is F perp R, or perpendicular R. I use the perpendicular sign to say I want the amount of F that's perpendicular to R. So instead of memorizing this, which you could, I can just say, all right, I want to have a force that's perpendicular to this radius, or tangential to the circular motion that will be caused. Okay? Another thing is you could, we'll see later on that you can rewrite this and say, or I can have some force and all I care about is the perpendicular part of R. How much R is perpendicular to the force? We'll see that's a different way of thinking about it. It's not as useful in many cases, but it actually is useful in a few, which we'll see later on. But the biggest thing is the amount of torque depends on the size of the force, how far away you push on it, and how perpendicular they are. That's what's important. You can either calculate that perpendicularity this way, or just look and see how much of the force is perpendicular. Or, and again, this is a little more obscure, but we'll see later, could you draw a line from the pivot point perpendicular to the force? And then how big is that line? Those would all give the same values of torque. Remember, qualitatively, this is rotational force. How do you get it? Depends on those three values.